everyone, this is Fatima, and here with me today is my student Adam.
Hey.
And today I'll talk to you guys about how to approach Hnmr questions. So Hnmr, or proton nuclear magnetic resonance, is a technique that's used to identify the structure of a molecule.
So how does it do that?
It does this by applying a magnetic force to the compound, causing the hydrogens in the compound to spin in a certain way. The frequency of this spin is recorded in the form of an NMR spectrum, which looks something like this. The x-axis of the spectrum represents the chemical shift in parts per million, and the y-axis represents the frequencies given off in hertz. And I'll talk more about this later on in the video. Each signal is recorded as a peak, as seen here.
So how can I read this chart to tell me what a compound looks like?
There are 4 general rules for reading an NMR spectrum. The first one I'm going to talk about is that the number of signals equals the number of types of hydrogens. The number of hydrogens is dictated by the environment that the hydrogen is in.
What tells us what the environment of a hydrogen is? What do we look for?
Good question. So the environment created by the atoms that hydrogen is bonded to will dictate the electron shielding effect on the hydrogen, and this will determine the signal received by the NMR. So when looking at the H environment, we're actually looking at the atom it's bonded to and what that atom is bonded to. For example, looking at hexane, if you take a look at the hydrogens I highlighted in yellow here, they are all bonded to a carbon that is bonded to 2 other hydrogens and a CH2. So I'm looking for what that carbon is bonded to determine the environment of the hydrogen in yellow. So the environment that all these yellow hydrogens are in are the same because the carbons that they're bonded to are the same. The hydrogens I highlighted in blue here are the same but different to the hydrogens in yellow because they are bonded to a carbon that's bonded to different things than the hydrogens in yellow. They're bonded to 2 CH2s. The hydrogens in green also are another set and share a carbon atom bonded to 2 other CH2s.
So in total, there are 3 signals that hexane will give on an NMR spectrum.
Exactly. 3 signals will look like 3 peaks on the NMR spectrum. Let's look at another example. Here's a molecule of butanol. I suggest you pause the video here and try to figure out how many signals you'd expect to find for butanol.
I got 4 signals for butanol.
That's correct. Here's the 4 environments for the different 4 hydrogen types, and here's a rough sketch of what you'd expect to find on an NMR spectrum of butanol. Rule 2 deals with integration. Taking the integral of these peaks will give you the area under the peaks, and we find that the ratio of the areas under the peaks are proportional to the number of hydrogens producing that signal. Let's look at an example. Here's propane, and it has 2 different hydrogen types, and therefore will produce 2 peaks on an NMR spectrum. Notice that one peak seems much bigger than the other. If we were to find the area under these peaks, we'll find that the ratio of the area of peak B to peak A is 3:1. If we took the ratio of the number of hydrogens in each type, we find a 6:2 or 3:1 ratio also. So the size or intensity of these peaks also gives us a hint at what our compound looks like by telling us the proportion of hydrogens producing the signal. Rule 3 is splitting, or also referred to as coupling. Splitting tells us the number of neighboring hydrogens adjacent to the one giving the signal. If we look closely at the NMR spectrum produced by propane, each signal is made up of smaller spikes, as we can see in the higher resolution version, and this is known as splitting.
So how exactly is splitting telling us anything about how many neighboring hydrogens that hydrogen has?
The answer to that question is given by the formula n+1, where n equals the number of neighboring hydrogens. So if we look at the NMR spectrum of propane, we find one peak with 7 spikes, which is called a septet, and according to our equation, n+1 is equal to the number of spikes. So if this signal has 7 spikes, we find that n is equal to 6, and therefore we know that the hydrogens giving the signal has 6 neighboring hydrogens. Indeed, we find that the hydrogen in blue here, giving the signal, do have 6 neighboring hydrogens in yellow. Looking at the next signal, we find 3 spikes, or a triplet. So again, according to our equation, n equals 2, which means that the hydrogens giving this signal has 2 neighboring hydrogens, which are our 2 blue hydrogens here. Notice also that the intensity of these 2 peaks are different. Remember in the last slide, we mentioned that intensity tells us the number of hydrogens belonging to each group. So just by looking at this, even though we're not given the area, we can say intuitively that the less intense signal here is coming from a smaller number of hydrogens, or our 2 hydrogens in blue, and the more intense one is given by more hydrogens, or our 6 hydrogens in yellow. For naming signals with spikes, when you have 1 spike, it's called a singlet, 2 is a doublet, and so on, and here are the general terminology used to describe these spikes. Our last rule is chemical shift, and sometimes the other rules are enough to figure out what a compound is, but the chemical shift of these signals also gives us hints about what our compound is.
What exactly does chemical shift mean? How does a chemical shift help me determine the compound?
Chemical shift refers to the position of the signal on this spectrum, where a hydrogen producing a signal with the higher chemical shift will be found more downfield of the spectrum, and a signal with the lower chemical shift will be found more upfield.
So, what determines if a signal will be more upfield or downfield?
The shielding of the hydrogen with electrons will determine where on the spectrum you might expect to find it. Generally, if the hydrogen has electronegative groups around it, like the hydrogen in carboxylic acid, for example, where the hydrogen here is right next to this very electronegative oxygen atom, that oxygen is going to want to steal electrons near the hydrogen, and therefore the hydrogen here will not be as shielded with electrons and be more deshielded. However, as we go further upfield, the signals here are from hydrogens that are more shielded with electrons. For example, in this far end, we have groups like CH3 or CH2 where there aren't highly electronegative atoms competing for electrons, and therefore the hydrogens here will have more available electrons that will shield them. And so the pattern of shielding can be shown by this arrow, where upfield signals are from hydrogens that are more shielded, and downfield signals are from hydrogens that are more deshielded by electrons. So we've seen a couple of examples now with compounds and what to expect for their NMR spectrum. But let's now put all those rules together in this NMR spectrum that we saw earlier in the video, starting with rule number 1. Number of signals is equal to the number of hydrogen types. Let's see if that's true for our molecule of 1,3-dichloropropane here. We learned previously that for determining the number of signals, we need to know the number of types of hydrogens we have. And here in yellow, we have 1 type because their environment is the same, and its signal is shown here. In this green box, we have a 2nd type of hydrogen, and its signal is shown here. So indeed, with 1,3-dichloropropane, we have 2 hydrogen types. We find 2 signals for its respective NMR spectrum.
So, what is that third peak I see labeled TMS?
Good question. TMS, which stands for trimethylsilane, is a standard used for NMR which is expected to be found at 0 parts per million. So it's used for calibration purposes, and it's often seen in NMR spectrums, but its signal has nothing to do with the signal given by our compound. We also covered integration. So here we have the area circled here under the peaks, and you're generally given the area or the ratio of the areas. The ratio of 23.4 to 11.21 simplified is about a 2-to-1 ratio. And so that means that the number of hydrogens producing each signal must be a 2-to-1 ratio. Let's see if that's true. Well, the number of hydrogens producing this first signal is 4 hydrogens, and the number of hydrogens producing the second signal is 2 hydrogens. And indeed, 4 to 2 is a 2-to-1 ratio. Now let's look at splitting. Taking a look at the hydrogens in yellow, we find that they have 2 neighboring hydrogens, which are in pink. So if they have 2 neighboring hydrogens, using our n+1 rule, we should expect to find 3 spikes from the signal given off by the hydrogens in yellow. And indeed, that's what we see in our NMR spectrum. The hydrogens in pink have 4 neighboring hydrogens, so we should expect 5 spikes from its signal, and indeed we see that this signal is giving 5 spikes. Our last rule we discussed was chemical shift. According to the table, the hydrogens in yellow fit the description I highlighted in yellow here, so we should expect to find their signal around 3 to 4 parts per million. Indeed, we in fact see that their signal is in this area at 3.75 ppm. When we look at the table, we expect to find a signal for these hydrogens around 0 to 2 parts per million, and looking at the NMR, we do have a signal around 2 at 2.2 parts per million.
But if the range is supposed to be between 0 and 2 according to the chart, why did it surpass the range and have a signal at 2.2?
Good point. These values are only estimated values for where you should expect to find the signal. In this case, we found a signal for these hydrogens slightly more downfield, possibly due to the highly electronegative chlorine atoms that may be pulling electrons toward it. And so the hydrogens in the middle here may be slightly less shielded or more deshielded by electrons. And we know that our more deshielded atoms are found more downfield. For that reason, we likely have this signal slightly more downfield. Now that we've covered the rules on how to read and interpret NMR spectrums, I've added a few practice questions. You're given the NMR reading for an unknown compound and the compound's molecular formula and the following information. Use the rules we've discussed to figure out the structural conformation of this compound. Pause the video because I will show you the answer shortly. I hope you got this as your answer. Here's another practice problem. So according to this NMR, your compound should look like this. Hope you guys found this video helpful. Thank you, Adam, for being a part of this video.
No, thank you for explaining this to me.
You're welcome. And I hope you guys found this video helpful. Thanks.